Okay, so I got a heat pump here. 134A is the refrigerant. Enters the compressor at 15 and 0, compressed to 160 and 60, and then I have liquid that enters the expansion valve, given it that. So I want to figure out the isentropic efficiency of the compressor as well as the coefficient of performance, right? So here's my compressor, okay, and then my expansion valve is here. And then I've got my heat exchangers 2 to 3. That's the hotter one, and then the colder one is 1 to 4. Okay. So what I need to go through again is I need to go find my H values, and I can look up most of these given here, right? I should be able to find H1, H2, H3, and H4 without too much problem. We'll go through that in a second. But the other thing, because I want to know the isentropic efficiency, I'm also going to have to go in here and look up my entropy here and set that equal to the isentropic entropy here to then look up H2S. Okay, so let's go ahead and get started. So we'll start at state 1, which is 15 psi and 0 degrees Fahrenheit for 134A. So I'm right here. So that's actually 22. Sorry, 134A. So 15 psi, 0 degrees Celsius. So I'm looking right here. I've got an H of 102.42 and an S of 0.2303. So go ahead and jot those down right now. And again, that H is 102.42. And then the S is 0.2303. Okay. And again, this S is the same as the isentropic S over here, because again, I'm trying to find the isentropic efficiency. I actually know what's going on in actuality. So I'll start by looking this guy up. So I'm at 160 psi and 160 degrees Fahrenheit. So we'll come over here to 160 degrees, or 160 psi, 160 degrees Fahrenheit. And I find that my H here is 129.78. Okay, so that's the actual H. Again, I'm going a little bit backwards of the way that we usually do it. So that's 129.78. Now what I want to find is what ideally it would be, where I'm going to use this pressure and this entropy, 0.203. So I'll go back here, and again, I'm looking for an entropy of 0.203, which, fortunately for us, is actually given to us right here. I don't even have to interpolate, which is at 140 degrees. Okay, that H value is 124.41. Again, that would be the H for an ideal compressor where there are no irreversibilities, which is not the case here. This is the actual. Again, I'm kind of doing this a little bit backwards. So let's go here to 160. It says it's a liquid. I do not have a liquid. And to prove to you that it's a liquid, let's go into the saturation tables at 160 psi, and you can see that the temperature at saturation is 109. Now I'm at 95, so I'm below that, so this is definitely a liquid. So the way we treat that is as a saturated liquid, because I don't have a table for a compressed liquid. So I'm going to go to the temperature 95 and treat it as a saturated liquid, which is 42.47. Okay. So again, because it's a liquid and I don't have a liquid table, I just assume it to be a saturated liquid at 95 degrees. Okay. Then I go across the expansion valve and H stays constant across that. So I'm left with that. So quickly, now I just calculate what my compressor efficiency is. And again, the equation for compressor efficiency is H2S. Again, that's the ideal compressor work over the actual compressor work. And when I do that, I find that I get a compressor efficiency of 80.4%. Okay. And then to find the coefficient of performance, okay, again, this is a heat pump, so it's Q out. Again, that would be the hot guy right here, the warm heat exchanger that I'm interested in, divided by the work of the compressor. So what that's going to be is H2 minus H3. Again, that is the heat dumped into the warm space, which is what I'm interested in for a heat pump. And then the work of the compressor is just, again, H2 minus H1. And I get a coefficient of performance of 3.19. So again, set your states, calculate what you want to find. Just remember that with a heat pump, what you're trying to do is dump warmth into a hotter space. So Q out over the work is what we're looking at for the coefficient of performance of that.